Hello everybody. In our last video we started graphing parabolas in a more general sense with a directrix and a focus, but we had done an example in which we graphed a parabola that opened up and down, okay, so or an upward U. And in this example what we're going to do is we're going to discuss what if we were to have a vertical directrix, okay, a vertical directrix and a focus that is oriented with this, but we say on this major axis here, this axis, but we'd say, okay, um, that the vertex would be the midpoint of these two things, and that the parabola itself would be a locus of points x, y that are the same distance from this focus, okay, and the parabola's directrix, equidistant, so this locus of points, and that our vertex is still at this point hk. So real quick, let's review the standard form of the equation of a parabola, or sometimes people call it the vertex form because it denotes the vertex. But we say anything that opens up and down, we say we have this quantity x minus h squared, and this is equal to 4p, where p is this directed distance from the focus back to the vertex, okay, and times y minus k. Noticing that h is always kind of respectively hanging out with our x quantity, and k is always hanging out with our y quantity. But something that opens sideways now, this is a little bit different from what people are used to, but we say this would be actually y minus k, so this quantity is being squared on the left. And we say this is equal to 4p times the quantity, the linear quantity, x minus h. So you notice again, just to refresh your memories here, we want the squared quantity typically on the left, or we just kind of get used to that, and we want the linear quantity on the right hanging out with our coefficient of 4p. Okay, so let's go ahead and kind of make up an equation here. We'll go with this one here. We'll go simple. We say y squared is equal to 3x. Now this is pretty trivial here, and I've kind of selected an equation in which our vertex is going to be at the origin, which is always, good to start with a trivial example and then build from there. But what we always want to start with is kind of trying to manipulate this to be in standard form. Now you notice I just drew an arrow pointing to the second example for parabolas that open sideways. And the reason why is because y, which we're used to being our dependent variable, dependent upon x, in this instance we say this is different. We say x is dependent upon y, or well, in this case we've not necessarily stated this explicitly in terms of y in terms of x because of the y squared, but this is going to open sideways. So let's go ahead and talk about getting this into standard form. Now you notice that there's an utter lack of anything hanging out with this y quantity here, which is our squared quantity. There's nothing in here, and there's nothing also hanging out with this x if we considered x being in a quantity here. So since that's the truth, rewriting this into standard form, it would look like this. We say y minus nothing really squared is equal to 3 times x minus nothing. And of course we could verify this by foiling this back out and just obtaining y, and distributing this and just getting our 3x back. But now that we've written it like this, it's very convenient because we're allowed to identify certain aspects of this parabola, starting with the fact that the vertex lies at h comma k. Okay, so remember, now this is kind of the weird thing about it. We like to have the squared quantity on the left, but h is the thing that's always hanging out with x, and k is always kind of chilling with y, and then we say this quantity here is kind of like our 4p. So the fact of the matter is this: we say the vertex v is at this quantity, or this point 0 comma 0. Okay, so that's nice, and just because we recognize that the y quantity is being squared, we know that this opens sideways. So here's the next thing we're going to find. We're going to find the directed distance from the focus to our vertex. Okay, so what we need to do here is we need to solve for p. And since, we'll do this off to the side here, we say, since 4p in this case is equal to 3, solving for p, we divide both sides by 4. We say p is equal to 3/4. So this is our second quantity that we typically always want to find. But since p is 3/4, and of course 3/4 is positive, and this thing opens sideways, what I can tell you is this: p must lie to the right of our vertex. So let's go ahead and get this show on the road here. We're going to go ahead and draw in our xy coordinate plane, because what's more fun than doing that? But how about I switch colors this time? I get so bored writing in white all the time. We'll go over to like a lighter blue. That'll be fun. Looks kind of like lavender, but we said, okay, start by graphing our vertex here, and our vertex was at this point 0 comma 0. Always good to label, and I'm labeling on the left because of the fact that I know that p is going to lie to the right. But I know this. I know that p lies 3/4 in a positive direction from our vertex. So we'll call this 1 unit away here. But I know that P is, and we can label this, guys. It is at, 3/4, comma 0. So now that I have this, I also know one more thing. I know that our vertex is always the midpoint between our focus here, our focus, and our directrix. And since this is going to open sideways, we have a vertical directrix at, if we call this -1 unit to the left, at this vertical line, and it's a good habit to label this directrix right here, but we're going to call this line x equals -3/4. Now that we have these things sketched in, we can go ahead and draw on this locus of points right here. So we say here is our parabola, and why not? Let's label this. We say this is y squared equal to 3x. Okay, so hopefully that helps.